Hi, today I'll be discussing my end-of-term project on modeling the adsorption of argon on graphite using grand canonical Monte Carlo. First, some introduction or introductory slides. Adsorption is everywhere. It's been widely used in industry for decades now to separate species such as water from air or hydrogen sulfide from syngas, synthesis gas. Nowadays, there's been an interest in using adsorption for CCS, carbon capture and sequestration, and accordingly, there's been a few materials or many materials that have been studied, such as zeolites, silicas, polymers, and metal organic frameworks, in addition to other materials like graphite itself. As you can imagine, with a wide variety of different materials and a wide number of variables that can be changed, such as the atomic doping, the structure, the pressure and temperature, to name a few, there's a large experimental workload that needs to be undertaken to actually rigorously screen these materials. To help assist with this, simulations can be used both to understand adsorption at an atomic level and also screen adsorbents. So different techniques such as MD, Grand Canonical Monte Carlo, or GCMC, and AI and ML have all been used both in conjunction and separately to help do this. Data from these simulations can be used to help build isotherms, which plot the fraction of adsorbent sites filled by the adsorbing gas versus the pressure. And they also have been used to help simulate or validate data such as heats of absorption. So in this presentation, I'll be talking more about how GCMC can be used to help simulate adsorption in the next few slides in the methods section. So methods. Now, again, in many adsorption experiments, what happens is the pressure is fixed and the fraction of sites filled is measured and the pressure is changed again, and these measurements are taken again and again and again. Physically, what's happening is that the pressure is fixed, so the chemical potential of the gas is fixed, and species can flow in and out of the adsorbents, so the number of atoms in the system can vary, and the temperature is fixed as well. In GCMC, the Gibbs ensemble is being simulated. So what happens is the chemical potential is fixed, but that's actually related to pressure via an equation of state, such as the van der Waals equation of state, the ideal gas equation of state, or Penn-Robinson. And so pressure is a proxy input for this system. The number of atoms is also changing in the system, so it can change so that the pressure equilibrates with the reservoir, and the temperature is also fixed, while the volume is also kept constant. So effectively, it models adsorption pretty well. Here we can see how to implement these number particle changing via insertion or deletion. So here's just a block of pseudocode to model first here at the top displacements, which are accepted or rejected according to whatever criteria is used in the NVT ensemble. Then for GCMT specifically, what we have is we throw a random number. If the random number is larger than or equal or less than 0.5, we attempt a insertion or rejection or deletion, respectively. We then find the requisite criteria or variables that are put into this acceptance criteria, such as delta E or delta U upon particle deletion or insertion, the thermal de Broglie wavelength, which is constant because temperature is constant, and the chemical potential, which is again fixed based on the pressure of the system. If that criteria is greater than, or if the criteria is greater than 1 or greater than or greater than a random number, then we accept and we update the number of particles accordingly. The criteria for acceptance and rejection for deletion and insertion, are shown below here. I'm taken from Franklin Smith's book. For my system, because we have both a fluid and a solid, we have to use two different potentials. So the fluid interactions are measured or modeled using the Lennard-Jones potential, which is self-explanatory. It's been used throughout this quarter for modeling argon-argon interactions. Meanwhile, argon-carbon interactions are modeled using the steel or the 1043 potential. This potential models specifically the graphitic carbon solid fluid interactions. And so here it's visually similar to the Lennard-Jones potential with a few different changes. One being that in front of the brackets we have rho C, density of carbon is involved in this potential, and we have instead of just pure argon-argon parameters, we have a solid fluid parameter, epsilon SF and sigma SF, which are the same, except that they're found using mixing formulas that I'll go into more in my report. And then delta is the intersplinter spacing of graphite. It's also used in this potential. The exponentials are different here. We have 10 and 4 instead of 6 and 12, or 6 and 12. And then at the end, we have a term that accounts for interplanar spacing effects for argon-carbon interactions. Now, for adsorption itself, to actually carry out the summation, I made a few assumptions just to simplify my code, and hopefully they're realistic enough to where there's no significant deviations from what I expect. So the first assumption was that the fluid in the reservoir can be modeled as a van der Waals gas. This is just to overcome any fictitious effects that would arise from an ideal gas being in contact with the Lennard-Jones fluid in the system itself. The second was that I only used 2 graphene sheets for simplicity, just because I was worried that first of all, that having a second and third graphite graphene planes would be too much for the system computationally, and I also modeled graphite or the graphene as a lattice, regular lattice, instead of a hexagonal shaped lattice, which is incorrect, but it's used for simplicity again. The next week I'll try and make that more advanced by making the initializing the carbon as a in a hexagonal manner. Finally, I assumed there were no periodic boundaries in the z direction. This is physicality only. Argon should not be able to suffuse to the basal plane of graphite, so it should be and because this is like again a slit-like pore, that should be physical for the system, and there shouldn't be any effects that cause us to deviate from a real system. So now here are some results that I gathered running GCMC on an argon system. So here are some representative plots of energy, pressure, and the number of atoms as a function of sweeps, where the pressure was fixed at 0.5 bar and the temperature at room temperature. So we see that equilibration is successful, and it occurs around 3,000 sweeps, and the pressure equilibrates to around what we expect from the reservoir pressure. It's around 0.52 or 0.53 bar, but although it's not within plus or minus 1 sigma of 0.5, it is within plus or minus 3 sigma of 0.5, as I'll show on the next slide. So we can say that it's equilibrated somewhat successfully. Finally, in the plot on the right, the rightmost plot, we have the number of atoms plotted with the number of sweeps, and this also equilibrates to around a constant value. There is significant fluctuations, plus or minus 10 atoms in the system. I'm not sure why the fluctuations are so large, but I hope I can fix this over the next week and figure out what's going on in my code. It looks like there's more deviations later on in the simulation, but it seems like it's coming back to a constant or average value around 85 atoms for these conditions, at least. So I also screened a variety of different temperatures and pressures to see what I could simulate my system at. So on the leftmost plot is the simulated pressure versus the reservoir pressure at 130 Kelvin, which is just below the critical temperature of argon. And the right plot is the simulated pressure versus the reservoir pressure at room temperature. Now the dashed line represents what I expect it to be based on what I've input to the system, and the solid line is actually just the simulated pressure. So at cold temperatures, at moderate pressures of 0.1 to 0.15 bar, I see significant deviations from what I expect, which likely arises from the fact that at those pressures, the potential energy contributes more to the system, and so I start seeing some weird deviations from gas-like behavior. At a higher temperature, I don't see such deviations. In fact, my simulated pressure agrees with what I expect up to around 1 bar, after which there is some deviation, but it's not too significant, around 10%. These error bars, for reference, represent plus or minus 3 sigma or standard deviations from the mean, as I calculated from halfway through the production run. So there's still progress to be made. I want to write a function in that could help determine the surface coverage of carbon at every step, so I can help build those Langmuir therms for a range of pressures. Those isotherms, by the way, look like what's plotted on the right hand side here. It's again surface concentration of the adsorbate versus pressure. Then I'll use that function and help find these isotherms and run it simulations at a range of pressures spanning around 1 order of magnitude. And I'll build a isotherm for room temperature. That's just because I can access a wider range of pressures at that temperature. And finally, I want to find a way to speed up my simulation because my simulation currently at 1 bar takes around 3 hours to complete with Numba. So if I can find a way to speed that up, I can run more and more points that'll help fill out the curve nicely. Thank you.